Great. Okay, so we're recording. So yeah, it's this week. It's Andrea who will be speaking on decomposition numbers for SL2.
Okay, so thank you all very much for tuning in on such a momentous day. So my job today is to discuss the decomposition numbers in natural characteristic for the group of SL2 over FQ. So before I get started with what exactly I want to do in this talk, let me just set some notation. So I'm going to work with, so the letter G is going to denote two things, and one of them is supposed to be this kind of bold-faced G. And they're just going to be the algebraic group, SL2 over FQ. And then I am going to use a regular G for the rational points. And for our talk, I'm going to fix a prime number P, and Q is going to be equal to P to the power of N. And I'll work with the letter T to denote the group of rational points of a maximal split torus in G. So the diagonal maximal torus, which, since we're doing SL2, is just going to be equal to these matrices. Okay, so the problem we consider works in the following context. So I'm going to work with a p-adic coefficient system. So E over QP is going to be a finite extension. And I am going to use the letter OV. So it is not supposed to be a sigma, although it looks like one. This is going to be the ring of integers. And I'm going to write K of E for the residue field. And I am going to work with a tacit assumption that could be made precise, but we're not going to need to do that, all these rings of coefficients are large enough. So all the representations that I'm talking about are supposed to be definable at least over E. And one of the consequences of this is that I want to be able to fix an embedding of a quadratic extension of FQ. So of FQ squared inside of K of E. And this embedding is going to be fixed throughout the talk and is going to be the one that I use in order to define Brouwer characters and so on. And the last piece of notation that I need is I'm going to write our K of E of G. And similarly for the other coefficients in here, for the Grothendieck group of finite length representations.
You mean an embedding of the invertible elements, maybe?
Right now, I really mean a field embedding, because later I am going to consider the action of this.
Okay, so you don't need yet. You are not fixing the. Okay, I see.
Yeah. So this in particular gives the thing that you want by restricting to the invertible element, but I want this to also be compatible with addition. Okay, and this is going to be the Grothendieck group of finite length representation of a group algebra over K of E. Okay, and given this setting, there is, of course, a reduction map going from RE to RK of E. So this is, I'm going to call this red. This is going to go from R of E of G to RK of E of G. And the way that this is defined, just to remind you, is so given a representation in characteristic theory, and I am going to use, in general, the symbol tau to denote such a thing. The way that you define red of tau, you just choose a G-stable lattice, OE lattice, tau circ, and then you just put red of t of tau to be equal to the semi-simplification of the mod P reduction. So two things to say. So here I should have said before that pi of A is going to be a uniformizer. Doesn't really matter which one in this talk. And here, of course, this representation is going to depend on which lattice you choose, and this is important in several contexts. But right now, we just take the semi-simplification, and then it's a theorem of Brouwer and Nesbit that is well defined. And the goal of this talk, well, the first goal of this talk is to say something about the decomposition matrix, which is just the matrix of this map. So the composition matrix of G. So in order to talk about a matrix, I need to choose two bases, and here I'm just going to use the basis of irreducible representations. So this is my matrix of red with respect to the sets of irreducible representations. So air E of G and irreducible K of G. And there's two things that I want to do in this talk. So the first one is to prove multiplicity 1 for this decomposition matrix. This talk does two things. So the first one is to prove that all entries of this matrix are in 0, 1. And this is what I mean when I use the expression multiplicity 1. And the second one is to give a number theoretic application of this, which is supposed to be a connection with Math-Emerton stock. And this application is going to be to Christoph-Breuil's lattice conjecture, which right now is a theorem of Emerton, G, and Savit, and is the motivation of much progress in this area of Mach-P Lagrange. And so goal number 1 is accomplished in a number of places, but the reference that I'm going to follow is the book by Bonafé, which is just called Representations of SL2Q. And throughout the talk, I am going to try to at least state how these results can generalize to more general groups. So they don't generalize in full. Everything that I am going to say depends quite heavily on the fact that one can just write down expressions for characters explicitly. But some parts of these are done for more general groups in a paper of Janssen on a reduction of the linguistic characters. And this is a paper in German that I am not going to. So I am not going to monitor the chat in detail, but I see that some people are asking questions. Oh, yeah. Yeah, if you want to ask questions, please just unmute yourself, and since there are not so many of you. Okay. So to get started, basically the proof of part 1 is just going to be an explicit computation using characters and Brauer characters. So the plan of this is going to be, I am going to write down, to remind you of the classification of all the irreducible representations that appear in here. Then I'll write down character formulas for such things. And then there will be a combinatorial part in which the two are compared. So it will be a direct computation with characters. Here I should have written conjecture. Let me just remind you that, so we've seen classifications of simple KAG modules. And it's going to be convenient to use the following one. So using the n-restricted characters. I'm going to write x sign of t for this. And in this case, these characters are just the same thing as integers from 0 to q minus 1. And they're just due to the fact that the way lattice here, they're just isomorphic to the integers. And I'm going to work with the following generator. I'm going to call epsilon, which just sends this matrix to alpha. And if I is actually 1 restricted, then you can compute the character of this simple module using the val character formula. In this case, you can actually do everything explicitly, and I'll just do that in a moment. And the valid character formula tells you well, the T character of a module corresponding to I, which I'm going to call L of I, they're just supposed to be equal to the T character of a val module. And in this case, you just get this fraction, where S is supposed to be the non-trivial element in the val group, and it's just a dot action. And here you do the computation, and you get the familiar formula, symmetric about 0. And of course, in this case, you can just do everything explicitly. Let me just get a new piece of paper.
So what is the index? What is I in?
So I, in this case, is just, oh, yeah,
I
it's
just-
just I contained in here. So x1 is the same one, but instead you just put n equal to 1. So instead of summing up until q, you sum up until p. So explicitly, well, it's a kind of general principle that the val module character is the same as the one for the dual one. And in this case, this induced module is just equal to the symmetric power. So this nabli is just semi of ft bar squared. And of course, there is an explicit basis for this, and you can just compute everything. So this is given by monomials of this kind, with explicit action of the matrices in the torus. You just get that alpha 0, 0 alpha inverse acting on this monomial, yi minus j. This turns out to be equal to epsilon to j minus I, evaluated at alpha times the same thing. So these are eigenvectors, and you can easily read the character and find that it changes by even numbers. And then finally, you use that. You can just find the characters of all simple modules just using the Sandberg tensor product. Gives the T character of Li for all I, all dominant I. And of course, this is very much specific to SL2. You're essentially using the fact that there is only one pure-restricted algorithm for the group. And so you can just write down all the characters explicitly. For ordinary representations or representations in characteristic theory, you of course end up using the linguistic theory, although in this case, everything is again very explicit. So in this case, you need to, the linguistic theory is something that is indexed by the conjugacy classes of rational theory. And in this case, you have 2 of them. You have 2 conjugacy classes of FQ theory in the algebraic group under the action of the rational group. And it's just due to the fact that the group is split and the val group has 2 conjugacy classes. And it's easy to write down explicit representatives for those tori. So one of them I've already told you what it is. And it's the diagonal one. And the other one is going to be a non-split torus that I'll write down in a second. So they are represented by T and this, which is going to be a non-split maximal torus. And there's a few ways of writing down what this is. And maybe the most conceptual one is just to say that it is the norm 1 elements in the action of now the multiplicative group of FQ squared acting on a 2-dimensional FQ vector space identified with FQ squared. So strictly speaking, this is just giving you one. They're just giving you a conjugacy class of Tora, but you can just fix one by choosing such an action, by choosing such an identification of FQ plus FQ with FQ squared. And I should say that just to make things even more concrete, this is going to be a cyclic group over the Q plus 1, and as splits and become conjugates, splits and becomes.
We can't see.
Sorry, yeah, conjugate to diagonal matrices after a quadratic extension. A quadratic extension. So over FQ squared. And corresponding to these two conjugacy classes of rational tori, you have two induction maps. So there are two defined at the level of Grothendieck groups. There are other ways of viewing them, but that's the one I'm going to use in the talk. So there are two deterministic inductions. First one I'm going to call, they're going to be indexed by elements of a vowel group. So the first one I'm going to call R1, and they're just going to be parabolic induction going from R E of t to R E of g. This turns out to be just parabolic induction. So you inflate to the Borel and then you induce. The second one is RS, and this goes from the characters of the other torus. Again, goes to R of G. And in this case, there is a normalization to pin down, and I'll just tell you what that is. So this is normalized so that the induction of a character actually has positive degree at the identity. So that RS of chi of 1 is positive. It is going to be a positive integer if chi is an irreducible character of a torus. And these have many properties, and the one that is going to kind of be important for us is that there is a Mackey type formula. This satisfies this essentially gives you the value of the inner product of two inductions in terms of the inner products of the characters you are inducing. And we're only going to need this for linear characters, in which case you can just write it as so Rx of alpha and Ry of beta. So there's going to be equal to 0 if x is not equal to y. So if you're inducing from two different tori, you get two orthogonal virtual characters. Orthogonal, not necessarily disjoint, but still orthogonal. And you get the following otherwise. If x is equal to y. So if you're trying to compute the inner product of two inductions from the same torus, then that's the same thing as computing this inner product on T or S, depending on what x and y is. And using this formula, it's easy, since you are in characteristic 0 and everything is semi-simple, it's easy to just write down a classification of all the reducible representations.
So RS normalization means you take the opposite, you take minus.
Yes, exactly. So you just, yeah, instead of taking the Euler characteristic of a cohomology, you take minus of that.
Okay.
Yeah. Right, so it's easy to write down a classification now. So I'm going to write down everything, assuming that Q is odd, and then I'll tell you how to change that in the case that P is equal to 2. The only difference is that all these tori are going to have non-trivial quadratic characters when Q is odd, and that is not going to happen when P is equal to 2. In this case, you get Q minus 30 divided by 2 irreducible principal series. By an irreducible principal series, of course, I just mean representations of a form are one of chi, with the assumption that this is actually an irreducible character. Then you get 4 irreducible representations from the reducible ones. So you get the Steinberg, the trivial, and 2 more representations. Are one of chi. Then you look at the other, the linguistic induction, and you find a similar numerology in which you have q minus 1 divided by 2 irreducible cuspidal series. Irreducible cuspidals, which are just the Rs of chi assumed to be irreducible. And then you have 2 boundary cases. The first one is the one in which you induce the trivial character, in which case you just get the Steinberg representations minus 1, which gives you nothing new. And finally, you get, at least if p is not equal to 2, you get a non-trivial quadratic character that you can induce. And this splits into a sum of 2 irreducible representations with multiplicity 1. So this gives 2 new cuspidal irreps. And if you want to work when p is equal to 2, then here you're supposed to take q minus 2 divided by 2, since now you only have one character that is fixed by inversion. And here you only get 2 of them, namely the trivial and the Steinberg. And here you get q divided by 2 of them. And you can sum how many you get and compare with the number of conjugacy classes, which is q plus 4 when p is not equal to 2 and q plus 1 otherwise, and compare that you get like that. This is a complete classification. There are, of course, more general principles to see that, but that's one way, at least. And now essentially you find that all the data that you need in order to make the computation are here already.
Andrea, can you slide your left-hand slide up just a tiny bit so we can see the bottom?
Thanks for pointing it out. Okay, so now to compute this reducible map, and this reduction map, sorry, what we need to do, so we need to use this data in order to write down the Breuer character. I'll remind you in a moment of what that is. Breuer character of an irreducible representation as a sum of Breuer characters of simple KEG modules. So, and if you are, the only thing that we're going to need about Breuer characters is that they are functions defined on the semi-simple classes of a group. They determine the reduction of an irreducible representation up to semi-simplification. And you can compute the Breuer character of a reduction of an irreducible just by restricting the ordinary character to semi-simple classes of the group. I'm implicitly using that for this kind of finite reductive groups, then the pure regular and the semi-simple classes are the same thing. And what I'll do is, so by the way, I've set up things. This is quite a lot of checking. So I'll do everything in detail for the cuspidal series, which is the only one that can be interpreted geometrically. I'll say something about that in a moment. So I'll do the computation for Rs of chi. So for these representations, very useful cuspidals, and write down the result for the rest. The general result. So in order to do this, I should, okay, the plan is going to be as follows. So I'm going to use the fact that semi-simple conjugacy classes are easy to classify in this case. So the group is simply connected, so you can reduce to the computation of geometric conjugacy classes. And in that case, they're just conjugated inside a maximal torus. So you find that semi-simple conjugacy classes are represented in TRS. And so the Brauer characters of a reduction of RS of chi is determined by its restriction to TRS. So the restriction of the ordinary character to T and the restriction of the ordinary character to S. And what I'm going to do is to write down generators for the groups of ordinary characters of T and S. So since these are have order coprime to P, it's the same thing to take ordinary Brauer characters. And then I'm going to write down these characters as explicit linear combinations of those ordinary characters. In order to do this, I'm going to write epsilon s for following OE characters. So this is given as a composition. So I've told you that S can be understood as the normal one elements in FU squared cross. So first I'm going to take the inclusion here. Then I'm going to take my fixed embedding. Into K cross. And then I am going to take that is the map usually known as the Teichmüller lift. And there is essentially the only multiplicative lift, the only multiplicative section of a reduction map that sends K cross into roots of unity. So there is a multiplicative character of S. And similarly, I want epsilon of T. So this can be sort of written in the same, as a similar composition, but it's also easy to write it down directly. So this is just what, just the map that takes this diagonal matrix and sends it to the Teichmüller lift of alpha. Okay. And of course, it turns out that these are the generators that we're looking for. So these generate a group of characters reducible E of T and reducible E of S. And what we're supposed to do now is to write down these restrictions as sums of these characters. I don't know if I'm supposed to take a break after half an hour, so this would be a good time to do that, but I can go on otherwise.
Yeah, let's take a short break. Actually, it'd be good to take it all in.
Okay, right. So
Okay, I think you can carry on, Andrea, if you.
All right, great. Okay. So the last thing that is needed in order to do everything here is to have a character formula for the ordinary characters. And the way that, since I'm doing the hospital case, there is a kind of direct way of doing this. So we have the following formula, which is right in the original paper of the linguistic. So there is a formula for, not for RS of chi itself, but for its tensor product with the Steinberg character. And this turns out to be just equal to the standard induction from the non-split torus. And of course, the Steinberg character is exactly what you need in order to compute the values of RS of chi on semi-simple classes. It vanishes elsewhere, but it's non-zero on all the semi-simple classes. And so using the known values of the Steinberg character, which in this case you can just compute by hand, you can just write down this piece of a character table. And you find that if Z is contained in T, then RS chi of Z is equal to 0 if Z is non-central. And this already follows from the Mackey formula, I guess. And otherwise, you just take the dimension of this representation times the value of chi as that. And for the other torus, if X is contained in S, then you find that RS of chi evaluated at X is equal to this sum, chi X to the Q. And this is if X is non-central. And otherwise, of course, you need to get the same thing. So RS of chi of plus or minus 1 is just supposed to be equal to chi of plus or minus 1 times Q minus 1. So now you just use a small combinatorial trick. So you notice that since, so in order to compute this restriction, in order to compute the restriction of RS chi of t, RS of chi to t, you need to find something that vanishes everywhere apart from the center. And of course, you can just quotient out by, the center of a group, of course. And of course, you can just quotient out by plus or minus 1, and then to take the sum of all the characters of that group, of that quotient group. And since the cardinality here is just equal to Q minus 1, you can just observe that the following equality is true. You just find that epsilon I t to the z, where I take this sum over I going from 0 to Q minus 2. This, of course, is just a normalization to say that you should take all the characters. And then you restrict to the even numbers there. And you find that this is equal to 0 if z is not equal to plus or minus 1. And it's equal to Q minus 1 divided by 2 if z is equal to plus or minus 1. In this case, assuming that Q is odd. And so the only thing that you have to do in order to get this RS of chi is just to multiply by epsilon in the case that chi is an even is an odd character. So another way of stating what I just said is that RS epsilon j of S restricted to t is going to be equal to, well, to twice the sum here, since here I want Q minus 1 instead of Q minus 1 divided by 2. And then here you're going to look at following sum. You just take all the integers that have the same parity as the exponent here. And here is like epsilon I of t. And something very similar is going to be true for the other torus. So you get essentially the same sum here, but then you need to account for this extra contribution that you get from the formula. So here you get the same expression, except that now you need to go up until Q, since now the torus has cardinality Q plus 1. And then you again take I congruent to J mod 2. Epsilon I of S. And then you add the contribution that you needed. Okay. And now you compare with the formula for the simple modules that we have given before. So to compute this reduction of Rs epsilon j of s, we use a Val character formula. And you just find that the prior character of delta I restricted to t. So I'm just going to rewrite what I said before in a way that looks a bit more like this. And you find that d is equal to minus I less than or equal than j less than or equal than I. Then you take j congruent to I mod 2 epsilon j of t. And similarly, the power of delta I restricted to s is again the same thing now. J congruent to I mod 2 epsilon j of s. Now I'm going to write by inspection, and then I'm going to actually do the computation. You can just find an explicit linear combination of Val modules that gives the delinguistic character. So by inspection, you find that this reduction, epsilon I of s, just equal to delta I minus 2 plus delta q minus 1 minus I. And once I tell you such a thing, it's fairly easy to check it. So you can just need, it's just a finite computation you need to make. So let's just check that they have the same restriction to t. And the way to do this is you just split the right hand side. So there are two summands, and I am going to split each summand into two. So I'm going to get 4 of them. I'm going to get 4 sums over j congruent to I mod 2 and 0 less than or equal than j less than or equal than q minus 2. So the first summand is what you get by restricting to positive j here. So you get sum for j less than or equal than I minus 2. Of course, here, this I should be an I minus 2. Then you get the negative ones, but the restriction of the inverses to t is going to be the same thing if you add q minus 1, since that's the order of the group. So the other summand I want to rewrite as the sum from j greater or equal than q plus 1 minus I, since the smallest one is going to be 2 minus I, and then I add q minus 1 to that. So I get q plus 1 minus I. Now I do the same thing for the other sum, and I get here j less than or equal than q minus 1 minus I. And then again the same thing, and I get j greater or equal than I. And now, of course, you notice that if you pair this summand with that summand, you get all the j's that satisfy this constraint, since you end up at I minus 2 and you start again at I. And you don't get I minus 1 since you want to restrict to the same parity. And again, you get the same thing for these two summands. So in total, you get precisely that thing right there. And a similar computation works. For restriction to S. And for checking a similar formula for the principal series characters. So, and for checking that a reduction of R1 of epsilon IT Well, it's very similar to this, but you take delta I instead of delta I minus 2. And here you just take delta Q minus 1 minus I. Okay. So before going on to the last step in finding the decomposition matrix, I just want to make 2 quick remarks. So the first one is that I have assumed in this computation that Q was odd. But actually, if P is equal to 2, then you find that the formula I have given for the restriction to the torus changes a little. Epsilon j of s restricted to T is going to be to the sum over all possible exponents without a parity condition. In this case, this is equal to epsilon I of T. And similarly for S. And if you go through the computation I have done before in this different setting, you find that the same formula actually works for the restriction. So the same formula for reduction of Rs epsilon is works. And of course, this points out to the fact that there's some kind of structural explanation as to why you get this kind of sums. And I'll just give a reference for the position of more general the linguistic characters. So the form, instead of just for more general groups and vowel groups, the composition of a linguistic character as a sum of vowel modules is known in terms of certain implicit invariants and was computed by Janssen. So it was given by Janssen. For any simply connected semisimple group. In terms of certain invariants defined by Verma by analogy with characteristics there. And the proof of this more general theorem goes through similar lines, except so it is still a comparison of characters, except that right now it is a bit more sophisticated in that you need to go through Frobenius kernels in order to establish the bridge between the linguistic characters and vowel modules. And of course, it's due to the fact that everything I've done so far is very much SL2 dependent. Okay. And now the last thing I have to do in order to convince you of that multiplicity 1 property is that, so to finish the computation. Of course, right now we have reduced to the well-known problem of decomposing vowel modules in terms of simple modules. So to finish the proof, one needs to decompose delta I in terms of simple modules. And so this audience hardly needs reminding that this is the domain of Lustig's conjectures. But in the case of SL2, you can just do everything by hand simply, and I'll just give you a recursive formula for doing this. And in our case, there is a recursive formula that you can find in Bonafé's book, for example. And I'm just going to state this. It can be proved by a comparison of characters again. So if you just write your integer I in base P, psi1 P plus dot dot dot, then you have that delta of I. So this is equal to, so there is going to be a sum of two summands, and each of them is going to be a product of two factors. So I get delta I naught. By this, I just mean the class in the Grothendieck group. Then you multiply that by, so you're supposed to take I minus I naught, you divide by P. So you just start from I1 now. Then you take a Frobenius twist. You restrict again to G. And then you have another summand, in which you take P minus I naught minus 2. And then you do the same thing. So you take delta of I minus I naught divided by P minus 1, and then you twist. And this formula has to be taken with a caveat, which is that delta minus 1 is supposed to be equal to 0. So using this formula, you can just write down the character explicitly, but for the purpose of checking multiplicity 1, you just need to look at what is the leading term in this decomposition, and you can just check that for every value of I that you can put arising from this sum, this resulting sum will have multiplicity 1 in the decomposition. Just a combinatorial check that you can make. So that concludes what I wanted to say regarding the multiplicity 1 property. Before moving on to the application, I just want to point out that the formula that I have given for the decomposition of a cuspidal character, so this one, actually can be given a geometric interpretation. And as far as I know, nothing similar is known for higher rank groups, and would be interested to know if anything like that is possible. I'll just sketch how this works. So this is due to Hastert and Janssen. And uses crystalline homology for the linguistic curve attached to the group. So in this case, you introduce a plane projective curve, which I'm going to call y of s, and they're just given by the following famous equation. And you take z to the q plus 1. This has a g action. This is given by linear transformations on x and y. So this is just the polynomial given the determinant, so you can let g act in that way, and s action, scaling these coordinates. And then you use the usual construction of the linguistic representations has to do with taking the étale H1 with QL bar coefficients of this curve, and then to decompose according to the eigenspaces of S. So what Hastert and Janssen prove is that you can do the same thing for crystalline homology and still get the same result. You find that the S eigenspaces in the H1 Chris of ys over the Witt vectors of K of E. So these realized lattices in RS of Chi. And just rapidly look at the chat since there seems to be. Yeah, so that's the SL2 curve. And then you use the fact that everything that I have written here can actually be done over a more general base ring, since this equation is given by integer coefficients. And then you find that since you've just constructed an appropriate smooth lift of ys embedded in the projective plane, you find that the mod P reduction of H1 Chris can be computed in terms of Durham homology. You just get H1 Durham of ys over k of e. Of course, the rhyme cohomology has a Hodge filtration. And the Hodge filtration turns out to be precisely what gives you this decomposition here. So more specifically, you find that Hodge filtration in the epsilon s to the minus r eigenspace, where r is just an integer, looks as follows. So it has the following filtration. So here you get the induced module. Here you get the eigenspace. And here you get the vowel module. So in this case, you do get a geometric interpretation of everything inside. I don't know of a similar interpretation that works for more general groups, although there does exist a formula for the linguistic characters in terms of vowel modules. So it would be interesting to know if anything like this can be done more generally. Okay. Are there any questions so far? Otherwise, I just give the applications I had in mind. Yeah, so there is a question by Tony in the chat saying that crystalline homology gives a canonical integral structure and canonical mod P reduction. The one thing I wanted to say about that is, so the one thing that I know works for more general groups is that it is possible to give a canonical integral structure in certain linguistic representations using rigid cohomology. In general, rigid cohomology does not have a canonical integral structure, but it is possible to build one for certain linguistic varieties using, and that's work of Grosse-Klöne. But I don't really know what happens with the reductions.
Why can't you do that with a crystalline cohomology for any with some kind of some log version?
I think it boils down to having to construct good equivariant compactifications for the covers and not just for the linguistic variety. And yeah. I don't know how good. So I know that Bonafarukia have such constructions, and I don't know what happens if you if you try to do it. Yeah.
Okay. Thanks. Yeah, it's not clear whether one can do it like that. Okay.
Okay. Right. So the last part of this talk is just the following application. That's right. Hopefully that's better. And essentially, so I'll just go quickly through some of the words that go into this. And this application hinges on the fact that the representation that I have called tau so this is something for GL2 rather than SL2, but the numerology is very similar, and multiplicity one also works for GL2. So if you have such an irreducible representation, and you know that it occurs in a smooth representation of a p-adic group, so and pi is an irreducible smooth representation of, say, Qp to the n, so the unramified extension of Qp of degree n. And you know that this space is non-zero. So you can regard this tau as a representation of this group just by the quotient map. And you know that this home space is non-zero. Then you know a lot about pi, essentially. Then the block of pi in the sense of Bernstein is known. And this is usually referred to as saying that tau is a type for pi defined on GL2 sub p to the n. And then now you can, so given this link, you can ask the following question. So you can give yourself a globalization of pi. So you assume that pi occurs as a factor of an automorphic irreducible representation. And I don't really want to say much about the context in which they show up, but so I'm going to call capital pi And for simplicity, I am going to work with a group that is compact at infinity, so there is no hard geometry to consider. So I'm going to work with a quaternion algebra over a totally real field F over Q totally real. Such that D is non-split at all infinite places. And then it turns out that pi has a natural integral structure. So has a natural lattice for the action of the Adels, for natural lattice for OE of GL2AF to the finite Adels. And one would like to know what is the induced lattice on pi. So this is a structure that occurs globally, and one would like to know what is the resulting local object here. So the induced lattice on pi. And Broy's lattice conjecture tells you what is the answer to this question, where you replace pi by tau. Gives the answer. For the lattice on tau. And the way that this conjecture was originally formulated was predicated upon knowing a classification of lattices. And this is precisely the thing that uses residual multiplicity 1 in order to be accomplished. So a main ingredient, so maybe I should just tell you how does the answer look like in this case. So the answer is given in terms of p-adic-Hodge theory for the restriction of the associated global Gilbert representation at P for the Gilbert representation of pi GL2E restricted at P. And this is the last thing I am going to say, is that a main ingredient.
Can we have that page back for 2 more seconds?
Oh yeah, sure. Okay. Main ingredient of this formulation is the classification of all lattices in tau. And this is what Matt was referring to when he was talking about a Morita theoretic interpretation last time via Morita theory. And this only works, so this is only manageable in the case that you have residual multiplicity 1. So the framework works in general, but classifying lattices in an irreducible representation in general is very hard when the reduction is complicated. So the classification goes as follows. So it's supposed to be tau. Classification goes in 3 steps. The first one is that by multiplicity 1 implies that for every simple module that appears in the reduction, so for all sigma contained in the reduction, there is a unique lattice, a unique up to scaling lattice. There's a unique scaling class in tau with irreducible cosocle isomorphic to sigma. With coq of tau sigma isomorphic to sigma. And then since tau is irreducible, implies that the maps between these special lattices form something that is free of rank 1 over the coefficients. Over coefficients. So you can choose a generator, iota sigma 1, sigma 2. Is usually referred to as a saturated inclusion between these two lattices. And then the last thing is that if now you choose an arbitrary lattice in here, then you can classify it by following groups. Maybe here I should have said z p to the n. Tau sigma tau naught with action of iota sigma 1, sigma 2 for all sigma. So what happens here is that this is again a rank 1 module. And so in order to give a map between two rank 1 modules, it's the same thing as to give an ideal, a fractional ideal. So it turns out that in order to classify a lattice is equivalent to give a collection of fractional ideals for OE. And that's the same thing as to give a collection of numbers. So by going through this classification, you can give a guess, a conjecture for what this lattice should be in terms of a collection of numbers. And it turns out that you can compute those numbers via the p-adic of Hodge theory of rho. And something similar can be done for SL3, since in that case, at least in generic situations, you do have a residual multiplicity 1, probably for GSP4. And it gets much harder in general. And this was one of the stumbling blocks that you ran into when you try to do more general groups. Okay, so that's all I had for today. I'm happy to take any questions if there's any.
So I mean, I'm a little bit confused, like just in terms of what number theorists really kind of want or expect in more generality. Like, I mean, this. I mean, I'm in no way an expert about lattices, but like, I mean, as far as I understand, like trying to classify isomorphism of lattices just for the symmetric group over QP is extremely challenging.
Yeah, I know. So in general, you wouldn't want to, in this case, you're lucky that you can actually classify them. In a more general situation, you would still want to prove that the induced lattice on pi is uniquely determined by the restriction of rho of pi, rho of capital pi to p. Essentially, what you would like to happen is that if you take this induced lattice on pi, and then you complete with respect to that, you get a Banach space with an action of the local group. And you would like that Banach space to be the same amount of information as the restriction of this global Gilbert representation to P. So you will still want a local global compatibility statement that maybe would be less detailed than what you can gain when you have a classification.
Okay.
So yeah, everyone is very much aware that classifying lattices in these so-called wild situations, it's very complicated, and that's a major stumbling block.
Oh, I'm sure number theorists don't need me to tell them that classifying lattices is hard. So that's
no, yeah.
But yeah, no, okay, that's good. I just wasn't sure what the kind of, but that I kind of okay. That seems like a more
so a
reasonable
possible
thing
end
to hope
game,
for.
a possible end game would be to hope that that lattice is still unique determined locally, even though you cannot write it down explicitly.
Yeah. Okay. Okay.
And actually, there are already some results going in that direction for GL3, for example.
But you said something about SN3. So I think for SN3, then the multiplicity 0 and 1 doesn't hold anymore, right?
So for SL3 and generic delinguistic representations, I would have said it does. Does it not? I'm pretty sure. I'm pretty sure generic meaning for RW mu. where mu is far away from the walls of the alcoves, I think that the multiplicity 1 statement is still correct.
I mean, for instance, if you look at SN3 9,
yeah,
then yes, I mean, like there are a lot of big characters where you have multiplicity 2.
Yeah, no, okay, of course. So you need conditions such as, so you need conditions on this to be something like this, essentially. So when 9 is too close to 3, I think, for such a thing to hold.
Yeah, so probably you want to use a Janssen formula in some
exactly. You need to,
region, right?
Yeah, you need to at least be in what Janssen calls a very generic situation, very regular situation.
Okay, yeah, and I guess this is only for the linguistic character, but not for the general representation.
Not for what? Sorry.
Yeah, I mean, like, I think you may hope to have the multiplicity 0 and 1 only for the characters which are the linguistic character RGT theta, right?
Yeah, but if you are in a sufficiently generic situation, I think you will find that the linguistic character is already an irreducible character. So for those ones, you actually get a result about representations, not just virtual characters.
Yes, but what I mean is that first of all, for those, then you have to be in some small region, and also you may have some So I mean, like when your character is not like a semi-sequent character, then I don't think that you can have the multiplicity 1.
Yeah, no, I agree with you. Yeah, I agree with that.
So you mentioned the filtration for characters of degree irreducible representations of degree q+1. Is that correct? What you gave was it in this case?
No, this one for the
filtration.
So this one.
Yeah.
So there's the ones of degree q-1.
I mean q-1. Yeah, q-1. So not the principal series.
No.
So have you tried to do something like that for principal series? Or
so
not?
I haven't, but I know that other people have, and they use very different methods. So of course, but
you could use you could do something similar.
I mean, in this case, with the linguistic variety, it's just a discrete set of points. So there is not much.
No, you can use them. You can use there's a surface you can use.
Oh, okay. No, I don't know about that. So if you want to say more.
So it's a covering of P1 times P1 minus the diagonal and the graph of the Frobenius.
Okay.
So what you see, if you take your group SL2 of FQ, you can realize it as rational points of the group you describe, but you can also take two copies of SL2 and take a Frobenius that acts by some kind of cyclic, okay?
Just some Weyer restriction.
XY is Y and X is a Q, okay?
Yeah. So something like this?
No.
Sorry.
Something, well, you can do it like that, yes, but yeah, sure, you can do it like that. Yeah, absolutely, yeah.
All right, great.
And then in this group, you can construct a usual Dunning. The Weil group is A1 times A1 now, so there are Dunning-Lustig varieties associated to 1 would be points, but you have S1, 1S, which will be like similar to what you've seen, but you have also the one for SS, and this one will be the one I described, P1 times P1 minus the diagonal and minus graph of Frobenius, and it's going to have a covering of order Q minus 1. And so there you will have, so it's now it's a in the H2 you will realize your principal series, your characters, and want us to see whether that's there.
Yeah, that's an interesting question, but I haven't thought about such a thing, but sounds like a very interesting question.
First, you would have to compute the normalization because originally you would have, it's a problem. Same problem as for higher rank. You mentioned you're going to have a covering. You're going to have an open varieties, and you have to take the normalization and hope the normalization is I don't know if it's good or not in this case, or whether you have to tweak it a little.
All right, I may try that computation.
Would it be possible to? Is that the same thing as if I took base affine space, so G mod U.
Mm-hmm.
So this would be a GM bundle over P1.
Mm-hmm.
And then I could take the quotient by the by FQ star.
Okay.
And so I'd get another surface which looks like it would probably give all the principal series representations.
Okay.
And maybe that's another description of what Raphael is describing.
Wait, careful. On that varieties, wait, are you taking?
Can you just say
it
what
might not
you?
be the same thing.
The
Can you
torus
say that again, Jordi? Like what you just said. You're taking G mod U.
on the torus on G mod U, the torus, the FQ star points of the torus is going to act trivially on the cohomology because the action extends to the connected group, to the connected torus, to the rational. So you won't realize non-trivial characters of your torus in there. So Cedric, if Cedric is around, he can correct me. But I think he has thought of these things more than me. But I think if you start with G mod U, and if you quotient that, I mean, you get covers, but cohomology is going to vanish most of the time. The cohomology is going to, you'll have covers of your quotients, but for non-trivial character of the torus, the cohomology will vanish. I think. So this variety I was describing, you can describe it directly by taking it's something inside G mod B times G mod B. I mean, if you take a Dunning-Lustick variety associated to an element of the red group or positive red group, that's a particular case where you take here S times S. And this generator of the center of the pure red group, positive generator, you can always take the corresponding Dunning-Lustick variety as a substitute for the finite set GF mod BF, G of FQ modulo B of FQ. So that you have always this substitute. And I don't know if people have tried to look at the mod P, the Durham or log-Durham or crystalline cohomology there. I might have, but I forget. I didn't, I don't remember. Yeah. But it would be something to check. There are many varieties you could use even for these cuspidal ones. And I don't know if the Hodge filtration is always the same or if you get different filtrations or different lattices. I don't know if people have looked at that. I mean, it gets harder as the varieties will have dimension, will have odd dimension. So next case is three-dimensional.
The other thing that you use in this case is that the variety is actually a hypersurface, and so there are methods for computing the Durham cohomology in terms of the Durham cohomology of the ambient space. And then you end up realizing these objects via coherent cohomology of a projective space. So I don't know if anything like that can be done in general, but it's certainly worth looking.
Maybe one more thing that could be very stupid, but like if I just look at the induction of the trivial representation, so the principal series for the trivial character, I can realize this as the global sections of a direct sum of skyscraper sheaves at the rational points of P1. And now this has a resolution via two line bundles. Like two equivariant line bundles. And then I think you get the the kind of decomposition numbers for this principal series from this resolution in the same way that you were describing. And I was just wondering if you could, because you can also put a different equivariant structure on the direct sum of these skyscrapers to get the other principal series representations. And maybe the same thing would work.
I'd have to think about that. So just to be explicit, what are the line bundles that you were talking about in this case in the resolution?
Oh, it's just like O and then, so O surgex onto the direct sum of the skyscrapers and the kernel is like the ideal sheaf of Q plus 1 points. I remember Matt explained this example a few years ago to me. I just thought it was It's so nice.
Yeah, I never tried to make this work for principal series, but yeah.
Well, like a direct analog of that for any n. So you look at the action of Z and Q, right, on the projected space, right? Then you get a doubly transitive permutation representation, and then you want to look at the decomposition numbers for that representation. I think it's a very hard problem, and I think maybe Zaleski and Supunenko, I don't know whether they found only involved decomposition numbers or maybe some fragment of it. But I mean, like, yeah, I mean, you can do it for when you Q is the prime, Q is the prime, and when Q is the prime power, then it's everything becomes so complicated. Yeah. And I assume that n is greater than 2, of course. Yeah.
Okay.
So is it possible to give some idea of like why number theorists care so much about pinning down this lattice? Is it like you get information about congruences or something, or? So
that's one way of looking at it. It's just that one would eventually like to know that the lattice in the whole in pi is locally determined, and then one would like to take the completion of pi with respect to that lattice, and to find a Banach space with an action of GL2 QP squared or QP to the n. And that Banach space should be should be the p-adic Langlands correspondent of the restriction of what I called rho of pi. So let me just So for simplicity, I am assuming that there is only one place of f above p. And then I would like to do what I just said to complete pi with respect to this lattice. And then I would like to say that Banach space is the p-adic Langlands correspondence of rho of pi restricted to the local Galois group. And so one would like to know in particular that this thing here is uniquely determined by this restriction there. And one way in which you could start studying that question is to see if at least the lattice that is induced on the type of pi is actually locally determined. And Broy's lattice conjecture gives you a formula for that lattice in terms of these numbers I was talking about that can be computed via the Dieudonné module of rho of pi. So that's this conjecture already gives rise to a very rich picture in that many invariants appears and so on, but that's just a tiny part of what one would like to be true eventually. So it's just viewed as evidence of what people would like to happen. And I should say that what I just said about computing the lattice and proving that is purely locally determined is actually a theorem for GL2QP. So if instead of looking at quaternion algebras and so on, you just look at GL2 over Q and then you take the complete homology of modular curves, then everything is a theorem due to Emerton, Kazin, and Colmes in various portions. Okay.
Another thing, this is really stupid, but I totally missed where multiplicity 1 came in at the end.
Yeah.
Like so what was the bit where you used it?
It comes in 2 places. So explicitly here, when you say that there is a unique scaling class of lattice, a unique homothetic class of lattices with irreducible Kozloff isomorphic to sigma. And then it appears in here. So it is not in the statement, but the way that you prove this is essentially to prove that this tau sigma has to be the image of a projective envelope of sigma inside of tau. And then you essentially consider the category that Matt was talking about. So the one that is the abelian category that is generated by lattices. And you prove that these tau sigmas are actually projective objects in there. And in order to prove that they are projective objects, you again end up invoking multiplicity 1, I think.
Mm-hmm.
So it shows up in 2 places. Yeah.
So can I actually just ask that? So this is a bit so you were talking about GL2QP. I mean, yes. About this. So you're looking at something. You're looking for something which is non-split at the infinite places, like how many?
In this case, I was looking for something non-split at infinite places, just for to simplify the discussion.
I mean, are there many of these things? I'm only thinking about, because I think for GL over FQ, there's like
so if you
splits
are
everywhere, like there are nothing interesting happens for over the finite field.
You're essentially asking for a classification of quaternion algebras over number fields, and just by global class field theory, you can do that just by specifying where the quaternion algebra is supposed to be non-split, and you can just the only constraint that you have is that the number should be even. So you can just do as many as you like.
Yeah. Okay. So there's a ton of them. Okay, thank you. No, exactly. My brain couldn't process working over QP. Thank you.
Of course.